Okay, so let's continue with the next session. David
Yeah.
Sánczez from University of Zurich, and he will talk about dark energy survey and some statistics, I guess. Okay.
All right. Hi, everyone. I would like to start thanking the organization for this opportunity to share latest progress on the dark energy survey and how we constrain cosmology with the combination of weak lensing and galaxy clustering. This is the 3x2 point. My name is David Sánczez. This is work I started helping during my PhD, and now I'm a postdoc in UCH, and I will be presenting on behalf of the DS collaboration. So far, we live in a universe which is accurately described by a standard model of cosmology, with a dark energy component which is pushing the expansion of the universe, fighting the gravitational collapse which is sourced by matter. If we want to learn about the universe, we can study the growth of the structure over cosmic time. We can go to the early universe and study the CMB through the AS parameter, the amplitude of the primordial scalar density fluctuation. And if we go late universe, we can learn about the universe with the galaxy surveys. With the galaxy distribution and the matter distribution, we can study spheres of radius of 8 megaparsec in the so-called sigma parameters. One of the strongest ways to learn about the large-scale structure is using the weak gravitational lensing effect. This is an effect produced by the deflection of the photons of very distant galaxies, which are interacting with the gravitational potential of the large-scale structure. This way, the shape of the background galaxies is distorted by these foreground lenses, and what we obtain in our telescope are the following, these distorted shapes. This effect is produces a very weak pattern, which is around 1%, and is also contaminated by other effects such as the intrinsic alignment. So this way we can decompose the shear signal into some gravitational component, intrinsic alignment, and knots. Given that the amplitude of this effect is so small, this requires averaging over millions of galaxies. So this points to the necessity of this very wide galaxy surveys. So how can we summarize all of these field level information from the matter density field and the shear field in two-point statistics to be compared with the likelihood with the theory? So by assuming that the matter distribution is mostly Gaussian, which is for the scales that we are using is very not, we can summarize all that information on the field in two-point correlation functions. Similarly, as we want to learn about how this grows with the cosmic time, we need to slice in different redshift beams. For example, one case is the two-point correlation function of the cosmic shear. This is a spin-2 field in real space, so we need chi plus and chi minus components, and each panel what shows is the correlation of the shapes for each tomographic redshift beams. This way we can summarize the field level information to two-point statistics. And as I mentioned in DS, we are developing a 3x2 point analysis. We are combining weak lensing and galaxy clustering, but where does this name come from? So first we have cosmic shear, which is the correlation of the source shapes, the galaxies in the background. This is proportional to the amplitude of the matter power spectrum. Then we have galaxy clustering, which is the correlation of the lenses positions, and this is again proportional to the amplitude of the matter power spectrum and also the galaxy bias square. And finally, we have the galaxy-galaxy lensing, which is the correlation between the position of the lenses and the shapes of the source galaxies. This linearly dependent with the galaxy bias. Galaxy clustering and galaxy-galaxy lensing together conforms the 2x2 point, and all together is the 3x2 point, which is a very sensitive probe to learn about the nature of gravity and dark energy. And the best constraint parameter is this S8 combination, this multiple of sigma and omega. So this is a very robust analysis in which by combining all together here, we can see the posterior of S8 and omega m from cosmic shear in black, dashed line is 2 times 2 point, and altogether 3 cross 2 point. By combining the 3 different probes, we can break the degeneracy in the posteriors. So we are applying this methodology with the dark energy survey dataset. This is the flagship stage 3 photometric galaxy survey, which measured a million of galaxies with 570 megapixel camera from Cerro Tololo. The observations were carried out from 2013 to 2019. And for the weak lensing analysis, we are using the wide field footprint, which is 5,000 square degrees, observed in 5 photometric bands, up to a limited magnitude of 24 in the eye band. With this dataset, we can deliver both growth structure analysis and geometry analysis. So now we are in the point of analyzing the final 6 years of data, which encompasses shapes and position of more than 140 million galaxies. This final data set compared to previous iteration of the catalog mean that we are pushing to deeper redshift, and that is translated in a 50% higher source density. All right, so now landing into DSY6 3 cross 2 point as the final analysis. This is a huge collaborative effort. It's coordinated by Martin Croce and Matthew Becker with several analysis teams building the different pieces of the pipeline. There are more than 50 active contributors spanning many different time zones. We have Gisela here, who is also working on the analysis, and we'll talk about shear ratios. And here you can see us in the different workshops happening during this time. The final GR6 analysis is built on the expertise of previous DS efforts, starting from the science verification time. From 2013, we did the Y1 and Y3 cosmology, and now we are aiming to deliver final cosmology results. In the Y6, there are many auxiliary papers which are going to be out with the main results, such as the treatment of the color-dependent PSF modeling. This is a paper by Theo Schut, which is already out. The treatment of the modeling on small scales, or the photometric redshift uncertainty calibration. These are all papers that are going to be out soon. And just to have an idea of how complex is this kind of analysis, this is a flow chart of the whole analysis, starting from the data taking, galaxy calibration, producing the shape catalog, treating blending, estimating redshift distribution for galaxies, doing performing the 2-point function measurement, doing the theory part, choosing which is the optimal way of analyzing the data to finally obtain the constraints on omega m and sigma m. So in the coming slides, I'm going to talk mainly in what our team is being focused, which is, all right, we have to find and design the optimal way to analyze this data in a robust way. So what are the analysis choices for the DSY6, and what is the philosophy? The main idea was to push the analysis to smaller scales. So this effort, this modeling effort, was led by Agnieszka Ferte, Jonathan Blazek, and myself. And the goal is to build a likelihood pipeline, compute the analytical covariance, and validate all the modeling choices. All of these while blended, so totally aseptic from the data. We're not using at any point the data. And just to mention a few highlights of the differences with respect to previous analysis, we are computing now the Mate power spectrum with HM code 2020, by also including some fixed harmonic feedback signal with the parameter of HM code, which is log TAEN fixed to 7.7. We are sampling over a flat prior on the neutrino mass, and we will also deliver linear and non-linear galaxy bias results, so two kind of analysis and parallel. For the intrinsic alignment, we will optimize the parameterization for each analysis. For the cosmic shear, we choose to show results from nonlinear alignment and tidal alignment and tidal torquing. While for the 2 times 2 point and 3 cross 2 point, we opt just to show results with that. In those scales in which these systematics and small scales contamination is not correctly described, we are applying scale cuts. And this way we can go In the linear analysis, down to 6 megaparsecs, and for the non-linear analysis, we can go down to 4 megaparsecs. And the relevance of having under control this contamination can be seen in this figure. When constraining and showing the posterior on the amplitude of the fluctuation and omega m, analyzing different signals with different contaminations coming from baryon feedback or galaxy bias, if we don't have them under control and we have some leakage of this contamination, this can fool us and move our posteriors in a non-controlled way. So for that, we have to define and validate our scale cuts in order to say, okay, once we get to the data, we are gonna present robust and unbiased results. To check the philosophy of how this is done, we can focus on the first panel. For the 2 × 10⁻² analysis, we study the posterior on S8 and omega m, and we analyze and plot posteriors from the analysis of contaminated signals, so some baryons, some galaxy bias. But for the analysis, we apply the baseline choices and plot compare with respect to the baseline contour in black. Markers here are the mean value of the posteriors. And the main test is, all right, if the markers are within the 0.5 sigma threshold, the 0.5 sigma contour, these scale cuts are working fine and we can go ahead. All right, so now we can move to the forecast. This result, so far we have our data blended. This is just forecast with synthetic data. And these are posteriors on S8 omega m from cosmic shear in dashed lines, 2 × 2 in solid magenta, and the black contour is the combination in 3 × 2 point. What we find is more than a factor of 2 increase in the constraining power measured by the figure of merit, so the inverse of the area of the ellipse, with 3 × 2 point with respect to shear alone. So we see there the power of combining cosmic shear with galaxy clustering. 3 × 2 point is very robust to systematics, and in the way, we can learn about intrinsic alignment and galaxy bias. And what to expect from the SY6? So these are results from linear galaxy bias. We see here posteriors from omega m and S8 from real data change from Y1 analysis, from GR3, and the forecast from GR3. You can see how the contour is smaller here. We are gaining a factor of 2 in constraining power compared to GR3 in a scenario of a more complex parameter space, which we have now in our analysis. In our MCMC, we have more than 53 parameters. So just as a caveat or some takeaways from the learning process of the Y6, there are many, but I will just highlight 2 of them. One of them is something called projection effects. It's the main character in my nightmares right now. Is the following. Imagine you produce a signal for which, or a universe in which you can measure the 2-point correlation function for some known input values. You can find them here in the dashed line. You run the analysis, assuming, okay, I know how I have produced it, I know the values. If I do the same and just analyze, I need to obtain the same. But in the presence of mildly non-constrained parameters, in our case, neutrino mass and galaxy bias, and due to the fact that you're projecting a 50-dimensional space into 1D or 2D, you can find this shift, this distance between pink and red lines. This is one of the main issues we've been finding in the validation process. Second one is something I'm sure you are familiar with, is the extensive and computationally expensive Markov chain Monte Carlo chains. These are very expensive. There is literature to find solutions like using multiple spectrum emulator and optimized sampling, or any other ideas that could happen in the way. And just if I have some time, the other day I was in a conference and they were saying, it was a panel discussion, is if you had infinite amount of money, what would you do? And they were saying, I would put an observatory on the moon, I would just buy the receipt for the dark energy, and I was just thinking, I would just do MCMC to be instantaneous. That would be amazing. So this is an estimate by Agnes-Perte on how many CPU hours we have burned to do the scale cuts validation, and it's 1.3 million CPU hours. So this time, this kind of challenges and many more we can chat on the coffee break are the different things that would do a 3x2 point with Ruby, LSST, Euclid, Roman, feasible and successful, or something we it's going to be very hard to do. I will just leave here with the conclusion. So DS has set the standards for the 3x2 point analysis, and the forecast constraining power is surpassing Y3. We have many analysis improvements. The constraints on W and lambda CDM are going to be presented by the end of the year, and we also will be releasing results on beyond lambda CDM analysis. The methodology provided here is going to be a milestone for Euclid, Roman, and Rubin analysis. And tackling all of these challenges I commented in the final slide are of high relevance for present stage 4 service. So yeah, if you have any question or you want to chat about this, please contact me on the email or in the coffee break. Thank you.
Yeah. David, question?
So, in my opinion, it would be a waste of money to spend all your waste of time and able to spend all on MCMC. But this is question: if you have 50-something parameters estimating in MCMC, does it make sense? I mean, are there degeneracies between those parameters, and how can you rule this out?
Right. So we have this is something. Okay, yeah, I wouldn't use my money on MCMC. And then we have 6 cosmology parameters, and the CDM 7 if we add WCDM. One could say intrinsic alignment with the full model is 4 more parameters, and galaxy bias is 1 or 2 per redshift beam. I think this is the one I would be interested in looking in the paper. Other one are calibration, like these are some model composition to calibrate redshift. So the correct answer would be from these 50, some of them are calibrated with simulations and have a Gaussian priority. So it's not that. If you check the number of effective parameters, would be number of parameters minus the trace of the product of the covariance of the posterior and the prior, you would see that we do have information to constrain like 1750 parameters, which are the real weight for the CMC.
Okay, thank you. More questions?
Yeah, thanks for an interesting talk. So, 20 years ago, we promised the funding agencies W0, WA. So we're very close to that now. But I wonder if one can take things around and ask, what can we learn about nuisance parameters which are interesting, such as intrinsic alignment biasing? I wonder what your perspective is. If we freeze the cosmology based on other probes.
Yeah, thanks a lot for the question.
What are the most interesting
things?
Yeah.
So when I was saying nuisance, I don't like calling nuisance intrinsic alignment galaxy bias because I'm really interested on those. So I think that in parallel to the 3x2 point with LSST or BL with DESI or full set with DESI, something we need to do in parallel with a similar effort is learn about intrinsic alignments and set as tightest priors we can for the 3x2 point. But in itself, galaxy bias, learning about galaxy bias and intrinsic alignment is interesting in itself. And I think there is some efforts like ECO-IA, which is a merge of stage 3 and stage 4 people. We've been doing nonlinear galaxy bias constraints here. And this is one of the first things I was try to have a look. So I totally agree. We should learn more about this intrinsic alignment galaxy bias.
Okay, thank you very much. Let's move to the